Okay, some final remarks on um, designing a lead controller using Bode, um, but with different performance specs in the first place. The examples I did before had two kind of performance specs. One was a steady state error spec, and the other was a peak overshoot spec. The steady state error spec led to a K naught. And the peak overshoot spec led us to a phase margin requirement. Once you had a phase margin requirement, we had steps to do everything else to find the pole and zero of the controller. So once you have a phase margin spec, everything else is the same. So we'll talk about instead of a steady state error spec, we're going to be given a closed loop bandwidth spec. And I'll show you how to go from that to a K naught. And instead of a steady state error spec, instead of a steady state error spec, we'll have a closed loop bandwidth spec. And instead of a peak overshoot spec, we'll have a resonant peak spec. And these only affect the first two steps of designing a lead controller. Everything after that is the same as we already talked about. So let's say we'll repeat example one, but change the spec. Here's the plant. We'll say a closed loop bandwidth of 6 radians per second and a resonant peak of 1.35. That's instead of a steady state error spec and a peak overshoot spec. Controller looks the same. It's a lead controller. Case of naught. All right. Here is the Bode plot of the uncompensated plant. And let's see. We want the crossover frequency to be 1/2 the bandwidth. Remember, the bandwidth is approximated as twice crossover frequency. So the desired crossover frequency is half the bandwidth. 6/2 is 3. Here's the omega equals 3 line. Here's omega equals 1, 2, 3. Where does the gain cross that line? Right about here. What is that gap? We'll say it's about 20 dB. Whatever it is in dB, this magnitude difference at crossover in dB, here's how to get the case of naught as just a number. Here's a formula for that. But 20 dB is easy, it's just 10. So we need a K naught of 10. The other thing was the phase margin. Now we have a resonant peak. That is the right side of this formula of this graph in the red curve. Spec was 1.35. I'll say that's here. Go over to the red curve, go down. It's about 45 degrees. That matches what we did the first time we went through it. But from here on, everything's the same. You know, once you have that phase margin, finding the P and the Z is still all the same process as we already went through. Here's the second example. Same transfer function for the plant. And now we have, let's see, a resonant peak of 1.5 and a closed loop bandwidth of 4 radians per second. So let's see. Bandwidth was 4, divided by 2, we get 2. 1, 2, that's there. What's this gap from 0 to where that blue line crosses omega equals 2? This gap. which by eyeball would be about, well, it would be about here. What is that in? Eyeball's not that good, it's probably somewhere between 10 and 15, 10 and 20. If we make it 14 dB, then it will match what we did before. So I'll say it's 14 dB. What's our K naught? I don't calculate the K naught here. Oh, bad me. I do this little calculation, but with 14 instead of 20. Bad me. Yeah, I didn't even calculate K naught. And I said the resonant peak was what, 1.5? So that's the right side, red curve, 1.5, come over to there. We need a 40-degree phase margin to meet the resonant peak. The rest of the steps are the same as before. And that ends everything to do with Bode. We did how to do a Bode plot by hand, how to interpret a Bode plot in a certain situations, and how to design a controller, specifically a lead controller, using Bode. We're done with Bode. Almost done with frequency, except we're going to do Nyquist. Save that for later.